Good morning, everybody. Welcome to the annual Masters of Engineering Bursary and Research Program that is hosted by PAMSA, the Paper Manufacturers Association of South Africa. My name is Samantha Charles, and I'm your facilitator, back-end producer, keeping things together, hopefully. And then we've got our experts today, our students, our 4 students who I'll introduce shortly. I'd like to invite the Executive Director of the Paper Manufacturers Association, Jane Maloney, to deliver a short welcome.
Welcome all of you, especially the students. We're excited to hear your presentations and we're looking forward to it. We've been doing this for a while, and it's very, very important to us to attract good talent, good skilled people, and those are all of you. So we are very pleased that you are part of our Master's Bursary and Research Program. Over the years, we have had probably 100 students doing this, and we've had a number of successes. And we believe that it's you that make the difference in our sector. So as I mentioned, we're excited to have you here. From a manufacturing perspective, it's incredibly important that we manage to valorize as much of the tree as possible and beneficiate any wastes along the way. And that's why the bioeconomy is so important to us. And it's so important that our production is sustainable. So you guys are part of a very exciting sector. We are absolutely not a sunset sector. There are people that believe that we are, but we are able to pivot. We are agile. We are willing to spend money on research. And although we have seen a decline in demand for paper and in the printing and writing grades, things like newsprint and magazine papers, we've seen an increase in demand for packaging grades. And on top of it, we have all the other exciting uses of pulp along the way. And some of those are things that you guys are working with. Apologies, when I say guys, I mean all of you. It's old school, and I know it's not politically correct. So a final fact that you can be proud of is we contributed 12.5 billion to exports in 2022. Our pulp exports contributed 22.7 billion, but because we don't make all the grades of paper, we actually import 10.5 billion rands worth of paper. So that gives us a positive input to the balance of trade, which means that we are incredibly important, especially when the rand is weak. So without further ado, thank you for joining us. Thank you so much to our academic partners. Thank you to our industry partners and to those of you that have been able to join us today. Thanks.
Thank you, Jane. First up, we'll have Mahlogonolo Mafela. She's the rose amongst the thorns today. She is investigating, experimental investigation of pulp vacuum dewatering using a laboratory suction box. Some big words for someone like me, but she knows what she's talking about. She's currently working at Impact, and she is doing her master's through the Stellenbosch University. We have Banele Keswa, who's talking about corrosion behavior in duplex stainless steel in pulp and paper liquids, and he is from the University of Witwatersrand. We've got Henry Leroux from Stellenbosch University looking at the use of spent pulping liquors as binders for chromite pellets. And then Zian Hoek from the University of Pretoria, or as we know, Tikkies, is looking at the drying of nanocellulose with the xanthan gum as a capping agent and its use for reinforcement in the mirror thermoplastic starch. And the reason why I don't do these presentations is because I don't know anything about it. And that's why we have these experts, our stars of the show today. And so, yes, they'll also obviously have some time to introduce themselves during their presentations. So I'm going to hand over to Mahlogonolo, and we can get going. So the rest of you can put your cameras off.
Hello everyone, my name is Nolo Mafela and I will be discussing dewatering of pulp by vacuum in the forming section of a paper machine with the aim of predicting pulp dry matter, which is the ratio of dry pulp to pulp suspension mass. This forms part of a study to optimize energy usage in a paper machine. The presentation and research would not have been made possible without the support of PAMSR, APACT, and my supervisors, Prof. Goggins, Prof. Toby, and Prof. Taihode. A little bit about myself before we start. I am a graduate from the University of Witwatersrand, where I obtained my Bachelor of Science in Chemical Engineering. I am currently a master's candidate at Stellenbosch University. My research interests include mass and energy conservation as well as systems optimization. I am currently a process engineering training at Impact Felixton. Most of you might remember me from last year. This presentation serves as an update of my research, where completion of my experimental setup has since been done. I have since vacuum dewatered my pulp samples, which enabled pulp dry matter predictions through data analysis. It is important to understand the mechanism of water removal in a paper machine to truly understand and study the energy distribution within it. It consists of 3 water removal stages. The first is the forming section, which uses vacuum to draw water out of pulp suspensions. It is further divided into 2 zones. The first zone uses gravity and filtration. The second zone uses vacuum, which is distributed by suction boxes. This zone is going to be the focus of today's presentation. The water is further removed in the press section by mechanical force using press rolls. The remaining moisture content is evaporated by hollow steam containing cylinders in the dryer section. This is the energy distribution between the different sections with respect to the amount of moisture content that is actually removed from the pulp. The forming section removes the most amount of water but uses the least amount of energy, where the pulp goes from a dry matter of 0.2 to 1% to up to 18 to 25%. The press section further removes the water to result in pulp dry matter of 56 to 64%. The water removal and energy consumption by this section is proportionate. The last section removes water to result in pulp dry matter of 90 to 95%. Although this section removes the least amount of water, it uses the most amount of energy, which is important to monitor, which is why it is important to monitor water removal in the forming section so that we can remove as much water in this section to prevent excessive energy consumption in the dryer section. The research was structured as follows. The main aim was to predict pulp dry matter after vacuum dewatering by a laboratory suction box, which was achieved through the following procedure. Pulp characterization of mechanically treated or refined pulp through parameters like your water retention value, which measures your water holding capacity, the fines content, which is a portion of small fibers in your pulp, as well as freeness, which measures how quickly the water is removed from the pulp. This is followed by suction box simulation, where an experimental setup was built to simulate a suction box in the forming section of a paper machine so that we could have pulsation effects, which is a pattern of vacuum exposure to your pulp, accurate dwell times, and adequate vacuum pressure within reasonable capacity, which was then followed by data analysis through empirical correlation of your variables like your vacuum pressure, dwell time, to estimate your pulp dry matter. The experimental setup is referred to as the laboratory suction box. It consists of 3 sections. The first section is the pulse generating area, which simulates exposure of vacuum to pulps with a particular pattern. Your vacuum distribution control using solenoid valves, as well as vacuum reservation using 3 vacuum reservoirs. Please draw your attention to the following short videos showcasing the actual experimental setup. So to test whether this experimental setup was enough to simulate the suction box in a foaming section, a comparison was done between two pressure profiles, an ideal pressure profile that was generated from meal data. Consecutive pressure drops can be seen, which essentially means exposure of vacuum to your pulp samples. This was compared to the experimental pressure profile, and the behavior of your laboratory suction box was found to be satisfactory, as similar pulsation effects were experienced experimentally. Operating conditions that were looked at include vacuum pressures of 19, 37, and 55 kilopascals gauge, dwell times of 30, 70, 110, 135, and 250 milliseconds. All hand sheets were made according to type PT205, with the following pulps in focus: bleached hardwood, mechanical groundwood, as well as new corrugated recycled pulp. All hand sheets were made to a diameter of 150 millimeters, a grammage of 100 grams per square meter, and all samples were collected at the highest refining stage. Dry matter predictions included analysis of your pulp type, vacuum pressure, and dwell time to predict pulp dry matter. The following empirical correlation was developed, where C represents the pulp dry matter, C naught represents the inlet pulp dry matter, and C infinity is the maximum pulp dry matter. T is the dwell time in milliseconds, and tau is the dewatering time constant. So your maximum pulp constant essentially represents the point at which dewatering of your pulp completely stops, and your dewatering time constant reflects the amount of dewatering time. The following graph shows your dewatering results at a vacuum pressure of 19 kilopascals gauge, where a maximum value of 14% was recorded for bleached hardwood pulp. Mechanical pulp was found to be the worst performing pulp. Recycled pulp achieved dry matter that was in between the two virgin pulps. The behavior persisted even at a pressure of 37 kilopascals gauge, where an even higher value of 19% was recorded, which means that increasing your vacuum level favors the dewatering of pulp. This is further proven at a pressure of 55 kilopascals gauge, where an even higher pulp dry matter of 22% was recorded for bleached hardwood pulp. The behavior of your pulp during dewatering can be explained using characterization data, briefly explained. As you remember, pulp dry matter is your dry pulp mass divided by the total slurry mass. The freeness is the pulp drainability measured in SR, where a high value essentially means that your pulp dewaters very slowly or poorly. The water retention value is the water holding capacity. Fines content is a portion of your pulp that has small fibers, which are less than 200 mesh, which is essentially 75 micrometers. So as your pulp dry matter increases, it is expected for your freeness as measured by the SR value to decrease. The relationship between the water retention value and your pulp dewatering behavior is unclear, as will be seen shortly. Your fines content being lower promotes your pulp dry matter. Bleached hardwood pulp was found to have the highest pulp dry matter and therefore a very low SR value of 37, a water retention value of 1.56, a fines content of only 25%, and so therefore a dewatering time constant that was very low, which basically means that it dewatered very quickly. Recycled pulp had a dry matter range that was relatively lower, the same freeness as the previous pulp, a water retention value of 1.39, a slightly higher fines content of 46.3%, which therefore meant that it had a slightly lower pulp dry matter range and a slightly longer dewatering time. Groundwood or mechanical pulp had very low pulp dry matter values, which is reflected in the SR value of 50, which is the highest recorded amongst all three pulps. The water retention value of the pulp is the lowest, which is unexpected, as you would expect this pulp to actually dewater quickly based on the water retention value. Therefore, it means that the relationship between the water retention value and your pulp dry matter is not as clear. It had the highest fines content of 74% and therefore dewatered very slowly, which resulted in high dewatering time. The research is beneficial because it prevents the use of expensive sensing technology. You can predict and monitor the moisture content in your foaming section without disrupting the manufacturing process. The empirical correlations that were developed are cost-effective and they allow for process optimization. Thank you very much for your time and attention. Are there any questions?
Do we have any questions for Mahlogonolo? If you're welcome to raise your hand and unmute. Well done. I can see a lot of hard work has gone into this. Nelson. Sure. Take it away. Morning.
Please go back to the slide before this one you have on screen.
This one.
Slide 8, yeah.
Yeah, just put it in slide mode so I can see the full data.
Oh, sorry. It's taking some time, I don't know.
But I'm curious about the difference between the bleached hardwood and the recycled pulp.
All right, sorry, just give me a moment. It's glitching.
Your water retention value drops by, call it 10.15 about unit. But your freeness is staying the same. Just explain that for me again. Why is that the case?
For which pulp?
The difference between the bleached hardwood and the recycled pulp.
So the difference in terms of water retention value and freeness.
Yeah, I'm surprised that your freeness remains the same whilst you're seeing a drop in water retention value. I'm just to understand why there's such a why there's no change in freeness.
So when you look at, oh sorry, did I cut you off there?
No, I mean, if you're retaining water, then your freeness. Okay, if you look in terms of Canadian standard freeness, I'm not an expert in SR, but you would, if the water doesn't drain, then it means it's staying behind. If you know what I mean.
Yes.
Yeah, but I'm surprised that your freeness value is still the same, even though you're dropping several units down with regards to the water retention value.
Okay, so the freeness values that I actually showed here is basically the average, which is a representative of your data. So if you look at the individual values for your recycled pulp and your bleached hardwood, depending on like the different samples that were tested, the freeness of your recycled pulp was actually slightly lower than your bleached hardwood. It's just that when I worked out the average, then it came out to that value. Because as you know, like with recycled pulp, there's a bit of variability in your data that you'll experience from sample to sample.
I see. But and then what is that error margin on that 37? So you can look at that in terms of freeness. What is that? Is that 37 plus or minus 2, 3, 4 units? What is the standard deviation on that 37?
I can't remember off the top of my head, but it was something plus minus 3.
Okay.
Yes.
All right. Thank you.
Yes.
Thanks, Nelson. Rosalind dos Santos, you've got a question for Mahlogonolo?
Sure. Hi, another impact person. How are you?
Good, good. How are you?
Thanks. Just checking if there's any vacuum dewatering technologies already on the market with the big OEMs that we use often, Velmer. How new is this type of drying? And we're going to put it in after our build presses. What's the thought?
Your question is to verify.
My question is to if there's already vacuum dewatering technologies on the market from some of our big OEMs like Velmer, like Velmer and Velmet, etc., etc. And if we're thinking of maybe putting this in after our belt presses.
There have been a few experimental designs that were explored in literature. I'm not particularly sure if companies like Belma have looked into simulating the laboratory's a suction box in the lab, but there have been a few designs that we also reviewed during the design stage of the actual setup that you see here. So the setup can actually be used for far more than what I have represented here. You can look at your paper strength, your wet paper strength. You can look at your additives. So it is something that you can use for a lot more than what I have presented here today.
Perfect. Sounds great. Thank you.
Thank you, Mahlogonolo. Then I don't see any other questions, but if you do have something that comes to, oh wait, Johan, Prof. Johan, you have something.
Yeah, thanks for the presentation. So obviously this equipment is meant to kind of develop a database of dewatering behaviors for different pulps and to compare the different pulps and the operating conditions of the vacuum dewatering in a lab setting so that you can ultimately implement those improvements on a real industrial paper machine. So do you know whether Impact has started developing this database and whether they're using the equipment to develop such a database, whether they've found anything they can use in an actual pulp mill based on this equipment?
I haven't heard of anything so far on whether they've started using the equipment, but I think there have been a few developments. Hopefully we can start doing some work by next year, early next year.
Great, thank you. Right, super, thank you very much. I'll now pass the baton to Banele Keswa, and you're up next. Thank you, Mahlogonolo.
My name is Banele Keswa, and I'll be presenting on can lean duplex stainless steel replace the currently existing Austenite stainless steel in the pulp and paper industry. So a bit about myself is I'm a young Black man born and raised in the townships of Soweto with an amplified interest in comics, cinematography, as well as science. I did my primary and secondary schooling in a neighboring township called Eldorado Park. And I then did my undergrad in chemical engineering here at Wits University. I chose corrosion as an area of study because of my curiosity to learn something new, particularly in the field of material science, considering that corrosion was not part of my undergraduate studies. So mitigating the effects of corrosion is a persisting challenge in engineering, and seeing that it cannot be stopped, I was then interested in how these mitigation tactics are applied in industry. So the basics of corrosion. So have you ever wondered why the colors of some metals change to a brown color with time? Well, this is corrosion. When these metals are exposed to air, which contains oxygen, and water, which contains, and moisture, which contains water or an electrolyte, they form compounds on the surfaces of the metals. And then after that, we describe the metals as being corroded. So let's ask ourselves, is corrosion bad or not? And yes, it is bad. Now, why? Because imagine if you have like a bridges beam that is experiencing corrosion, or a corroding chemical pipeline that would contain, let's say, hot acid. So if these structures were left unattended for a period of 5 to 10 years or even more, eventually something terrible will happen. That bridge would collapse, or that hot acid pipeline would leak or rupture, and that would lead to like a considerable loss of lives and large sums of money. So our industrial facilities, such as paper plants, use a variety of metals for their construction. And now, why the focus on the construction of these paper mills? So assume that you have wood chips that you need to cook to make paper. So to cook, you'd need a pot, you need water and heat, and then you throw in your wood chips into the pot with the water and let magic do its work. Now, from this analogy, your pot is then your pipes and digesters, while your heat is your heat, and your water in this case is your acid and alkaline pulp liquors that are used to digest the wood chips for paper making. So, and at high temperatures, these alkaline and acidic pulp liquids would eat through your paper and eventually cause you to stop your cooking process and replace your pot. And to stop and replace your pot, that will ultimately cost you time and money. So the motivation behind my research are the extensive corrosion problems that we found at the Mondi paper plant in Richards Bay. And we saw that various chemical storage and process units had succumbed to corrosion due to the handling of high temperature salt, acidic, and pulping media across the plant. So my research comes in because there are different kinds of metals that are used for construction worldwide. And these metals have different corrosion reactivities due to the diversity of their chemical makeup. And these metals, and now we've widely used austenite grades from the past up to now that replaced carbon steels from the 1980s. And they were and have been good, but their faults have been exposed as the paper industry has grown and been optimized. So the current corrosion problems currently persist on these austenitic metals. So which leads us to the newly invented grade of stainless steels, which are the lean duplex stainless steels. These have been used in a commercial building and construction industry. They offer good corrosion resistance, they are high in strength, and also they are light in weight. Now the question is, how would these fare in a pulp and paper setting? So 76 different process conditions for 3 stainless steels were done across the following experimental set. And at the end, I shall mention to you what the 3rd stainless steel is. So we can see that we have a sheet of metal that were cut into small pieces of metal, which were then connected to a copper wire. They were ground, cleaned, and then immersed in their respective electrolyte liquid medium, and then connected to a potentiostat that was used to measure the corrosion performance. And to the bottom left, we see a simplified view of an electrochemical cell. We see a working electrode as our sample steel, a counter electrode, as well as a reference electrode. And these were all connected to a potentiostat, which led to the following graphs being produced. So at the top, we see an OCP graph that was used to measure the stability of a passive layer that helps with corrosion protection. And then below that, we have a linear polarization curve that shows the corrosion behavior of that would occur on the surface of the steel or the metal. And then to the right, we have a cyclic polarization graph that further shows that if the steel will either experience thinning or holes on its surface as corrosion ensues. And this cyclic polarization graph differentiates itself from the former in that we see that it has the presence of a loop. And in the next slide, I shall tell you what this loop is. So these are just 2 examples of like the 76 conditions that were explored. At the top, we see like the behavior of a stable and not so corrosive liquid media such as green liquor relative to what's at the bottom, which is an unstable ionizing liquid media, which is hydrochloric acid. And both conditions were applied to the lean duplex stainless steel grade. So for the green liquor, we can see that in its OCP, we have a stable and smooth passive layer, while in hydrochloric acid, this passive layer constantly breaks down. And then for the cyclic polarization curves, which both have the loops that I previously talked about, we see both of them have it. And this loop is what contributes to the formation of what we call pits. And these pits is just a fancy word for saying holes on the surface of the metal. And with time, these pits get deeper and deeper. And as we can see that for the acid, the acid caused a significantly larger pit in the same amount of time than the ones we can't really see are caused by the green liquor at the top. So, and then over here we have what's this graphs. The first graph is the behavior of lean and austenite in sulfuric acid. And then the second graph below that is the behavior of lean duplex stainless steel in the pulping medias. So these graphs, I presented the corrosion rates in terms of millimeters of steel that were lost per year. And then I came to the following deductions in that in all the experiments that I did, the austenite grade suffers the most corrosion. And then the lean grade performed quite well in comparison. And then also what I saw is that the salt and hydrochloric acid on site led to the formation of pits on the surface of metals. We call, well, those pits, like I said, are just holes on the surface of the metal. And we saw that led to like leaks on the storage or process units that were found on site, and then supported by literature. The formation of these pits was due to the presence of an unstable chlorine ion in these substances. And then we come to another deduction based on sulfuric acid. So sulfuric acid, in contrast to the hydrochloric acid, instead of forming pits or holes on the surface of the metal, it induced metal thinning, not holes, but metal thinning over time. And then another deduction is that I saw that as temperature increased, the corrosion rate increased, and this was supported by the reaction kinetics theory. And in the second graph, which I said focuses on the lean duplex stainless steel in the pulp liquors as well as the bleach media, I found that the bleach media contributed to minimal corrosion rates, and hence I chose to omit it from this graph. And then we found that the green and white liquor were the most corrosive, and the black liquor stood out in that temperature did not significantly affect its corrosive abilities, and hence it stayed constant as temperature increased. And then to conclude, so the newly invented lean duplex stainless steel has and is cheaper than the currently implemented austenite grade that's found in the digesting units and pipelines on site. And then I've shown that the lean grade poses significantly better corrosion resistance than the austenite grade, and would serve as a good alternative in handling the black liquor, the green liquor, as well as the white liquor. And then moreover, so the results for the lean grade in salts suggest that all the NaCl, which is salts that are found on site, can be handled comfortably without severe corrosion consequences if it's handled by lean duplex stainless steel. And then furthermore, I then done tests in acid, and I found that acids contributed to large corrosion. And however, with the lean grade faring well against the austenite grade in all the conditions, I then included a third grade of stainless steel to mitigate the acidic conditions. This grade of stainless steel is the standard duplex grade of stainless steel, and it would mitigate against the constant leaks and welding requirements of storage vessels that are made up of PTFE-lined carbon steel that currently store acids. And with that, I'd like to give a huge shout out and thanks to my sponsors, Pamza and Mondi, as well as my supervisors, Professor Herman Potgieter, Dr. Michael Borderin, and Dr. David Whitefield. Thank you.
Thank you, Banele. Oh, there's a terrible. Coming back at me. Just mute yourself quickly. Let's see if it works. There we go. That's better. Right. So does anybody have any questions for Banele? Please do raise your hand, and then we can present those questions to Banele. Some round of applause for you at least. Ralph from Mondi, take it away.
So yeah, good morning, and thanks for the updates, Banele. Well done. Just a question. I can see on your slide where you put the graphs together showing the differences and so forth. Yes. If you look at the top, we look at the lean and the austenite differences in stainless steel. On your third slide, you mentioned the standard duplex one as well. So have you compared those as well as a question? And then the second one is, if you look at the graph at the bottom, you make reference to white liquor, green and black liquor, but nothing in specific regards to HCl, because that's the bigger corrosive component. Have you considered that as well compared to these graphs?
Yeah.
Thank you.
Sorry. Yes. I have done all of those. So due to like the number of results that I have, I couldn't fit them all here. But a comparison between all the three stainless steels were done across all the liquid media that I have. So these were 8 liquid media and 3 stainless steels at 4 different temperatures. And then we found that in the pulping media, as well as the salt media, lean duplex stainless steel fares better than the austenite stainless steel. And then in the most corrosive, which is your sulfuric acid and hydrochloric acid, although lean duplex stainless steel beats austenite, it still suffered quite a lot of corrosion due to these acids, and hence that's where the standard duplex stainless steel showed that it can provide itself as an alternative in handling the acid. And due to its expensive nature, I've just limited its application to the acids, because in the other pulping media, lean duplex stainless steel did quite well, and it's much cheaper.
Thanks for that, Panele. You touched on the second question that I basically had, and that was mainly around the costing side.
Okay.
So the differences in costing. So at the moment, everybody's using the normal stainless steel, the Austenite. So how does this compare differences in costing when you compare that to the other two variants? So just a question.
All right, when it comes to the costing of the Austenite, doing a bit of research, we've seen that Austenites, due to their abundance as well as their demand, they were somehow costed to be way more expensive than the lean duplex stainless steel. I would assume because the lean duplex stainless steel had not been known up till now, and hence it's still cheaper. And then when it comes to the standard grade of duplex stainless steel, that is way above both the Austenite and the lean duplex stainless steel. So hence, in essence, a solution can't be provided by one type of stainless steel, but considering the economics is that we can bring in a less cheaper metal than the currently implemented Austenite, as well as a slightly expensive metal, but for specific conditions which are related to acid, which would be the standard duplex stainless steel.
Thank you, Banele. We are now going to hand over to Henry Leroux and his presentation on the use of spent pulping liquors as binders in chromite pellets. So take it away.
Okay. So good morning, everyone. My name is Henry Leroux. I'm currently busy with the second year of my master's project at Stellenbosch University, and I did my undergrad at the University of Pretoria. I've always had a keen interest in the paper and pulp industry and how it works, having grown up around it for most of my life. And I'm also a firm believer in that no waste product produced by an industry is truly without any further use. And because of that, the project that I chose for my master's is the use of pulping liquors as binders for chromite pellets. You can go to the next slide there. So just a quick overview of what chromite is. Chromite is chrome ore. It's typically mined in quite a fine dust or powder. But the problem with this fine dust and powder is that it cannot be put directly into submerged arc furnaces. It can lead to damages to the equipment and to health and safety risks. So because of this, what you have to do is typically agglomerate it into something the size of pellets or briquettes before you can feed it into a furnace. So because of that, one of the first things I had to look into at the start of my project was the different types of agglomeration that are used. So in industry, what's typically used are ball mills and disc pelletizers. Now, these are quite big machines that through continuous movement mix the chromite and the binder and the moisture into pellets. However, these machines are quite a couple of meters in diameter, so they're not really feasible for any lab scale uses. So because of that, for experimental work, people typically use die sets and mechanical presses. So on the right there, you can see a picture of one of the die sets that I used in my project. And the way that this die set works is that it is a stainless steel cylinder where you can load your material into the middle there, and then you have a piston or a plunger that you place on top of the material. You then put this setup into a mechanical press and apply pressure with the mechanical press. Once you've reached your desired pressing pressure, you can remove the die set and open it up at the bottom and pop the pellet out the bottom by pressing on the plunger. Now, this method is quite slow and tedious because you're essentially making one pellet at a time, whereas with the industrial methods, you'd be making a whole bunch of batches within the hour. But you do have a lot more control from one pellet to the next because you are essentially have a closer control over the pressure that you use, and thus the density and the shape and the size of the pellets. So because of this, there's a lot less variation from one pellet to the next, which does make it very good for experimental work. So one of the other things I had to look into is the different production methods for these pellets in industry. The two main processes that are used in South Africa are the Outokumpu process and the Primus process. Now, the main difference between these two processes is that the Outokumpu process heats its pellets in an oxidative sintering environment as a pretreatment step, and the Primus process heats its pellets in a reducing environment to a high temperature as its pretreatment step. Because of this, the different processes also use different recipes, with the Outokumpu process using less binder and less reductants than the Primus process. So because very little research has been done before with pulping liquors being used with chromite fines, I decided to use several different types of pulping liquors from several different processes in order to determine which one could possibly work best. The specific pulping liquors that I ended up using are sodium lignosulfonate, magnesium lignosulfonate, soda liquor, and craft liquor. You can go to the next slide. So in order to determine which of these pulping liquors actually work best, I had to conduct several different strength tests. One of the first strength tests that I conducted is the green impact strength test. Now, the way that this test works is straight after I remove a pellet from the die set, I drop it from a height of 1 meter repeatedly until the pellet breaks. The number of drops it takes for the pellet to break is then known as its green impact strength test, or its green impact strength. So here you can see the results for both the Outokumpu pellets and the Primus pellets. Now, just the two big takeaways from these results are, firstly, that with an increase in binder mass percentage, you get an increase in the green impact strength of these pellets for both the Outokumpu and the Primus pellets. And also for both sets of results, the pulping liquors did outperform the industry standard binder option, which is bentonite. For the Outokumpu pellets, the industry typically makes it with 0.8% bentonite, and for the Primus pellets, they typically make it with 3.5% bentonite. So yeah, you can go to the next slide. I also conducted a indurated compressor strength test. So for the Outokumpu pellets, after these pellets are pressed from the die set, they are put in a muffle furnace and heated to 1200 degrees Celsius. Now this is done in an air environment so that oxidation is allowed to take place, because that's what happens in the Outokumpu process itself. And for the Primus pellets, I took them out and put them into a pyrolysis oven and heated them to 700 degrees Celsius. Now, this is done in an inert nitrogen environment so that oxidation could not take place, because that's what happens in the Primus process. It is important to note that ideally I would have liked to also heat these pellets to 1200 degrees Celsius as well, but unfortunately the machine that I had only went up to 700. So if you look at the results for the Primus pellets, even though it's not at the correct temperature, just from the results at this temperature, you can see that there's no significant differences between the different pulping liquors, and that they provide pellets with relatively the same strength at the same binder mass percentages. But they do outperform bentonite. So when you have a look at the Outokumpu process pellets, the results look a bit different. So there were two pulping liquors that outperformed both the other two pulping liquors and bentonite, and these two pulping liquors are sodium lignosulfonate and craft liquor. You can go to the next slide. So after I determined that craft liquor and sodium lignosulfonate are the two best performing pulping liquors for the Outokumpu process, I decided to do some additional tests on them. One thing that I investigated was using lime as an additive with these two pulping liquors. Now, in literature, I had found that people have used it before with lignosulfonates to increase the green strengths of coal briquettes. So I decided to see if I can replicate these results for chromite pellets, and if it would be useful for chromite pellets to also use lime. So from the green impact strength test on the top left there, you can see that it did increase the impact strength of the sodium lignosulfonate, like you would expect from literature, but it did not significantly increase the craft liquor pellets' strength. However, when it comes to the sintered compressor strength test of these pellets, there were very big reductions in the strength for both the sodium lignosulfonate and the craft liquor pellets. And what these results essentially mean is that adding lime as an additive is not feasible for chromite pellets. Now, I decided to also have a deeper look into craft liquor. And what I essentially decided to determine with this is whether it's the inorganics or the organic components of these pulping liquors that provide the strength to the pellets. So what I did with the craft liquor is I used acid precipitation and purification to decrease and further decrease the ash contents of the craft liquor. And basically, yeah, what the precipitation does is it precipitates out your organics. You still have a bit of ash in your precipitated lignin, but then through the purification, you further remove more of those inorganics. I also decided to do the opposite, where I partially ashed the craft liquor, and what this did was just burn off some of the organics, thus increasing the inorganic content. So from the results on the right there, you can see that for both the green impact strength and the sintered compressive strength, you can see decreases when I made these alterations to the KL. And what this essentially means is that you need both the organic and the inorganic components of the craft liquor to actually create pellets with sufficient strength. And if you only try to use one more than the other, you actually do result in decreases in strength. You can go to the next slide there. So another test that I did is the abrasion resistance strength test. And the way that this test works is after the pellets have been removed from the muffle furnace and the pyrolysis oven, they are put in an abrasion drum. And the way that this abrasion drum works is that it spins at a constant speed, and it has these 3 little lifter vanes that constantly lifts and drops the pellets as it spins. And these pellets then drop onto each other or onto the drum and continuously break down into fines. So what I did was I stopped the abrasion drum at set time intervals, and I took out all of the material and passed it through a sieve or a screen of 1.18 millimeters, and this screen is basically the divide between what is considered fines and not fines. So the abrasion resistance index of these different pellets was defined as the percentage of the pellet that did not pass through the screen and essentially stayed as non-fines. So I did these results, and the main takeaway from these results is that the sodium lignosulfonate and the craft liquor once again did outperform bentonite. But also importantly, what I noticed is that the order of these strengths actually resemble the order of the sintered compressive strength test, or the indurated compressive strength test that I mentioned earlier. And because of this, I decided to do a linear regression analysis on these different sets of results. And what I found is that there is quite a strong correlation between the sintered compressive strengths of the pellets and the abrasion resistance strengths of these pellets. Now, what this means is that for future work, it is not necessary to actually do this abrasion resistance strength test, because you already get a good enough indication of the strength from the indurated compressive strength test, and you can already see whether one binder is better than the other from that test, and it's just not necessary to do the abrasion resistance strength test. So you can move on to the next slide there. So what do my results actually mean for industry? So because my results were very positive overall in that the pulping liquors did outperform bentonite, it means that further research should be done. So obviously all the work that I did was on an experimental scale with experimental agglomeration equipment. And because of that, further research or further results should be done for industrial scale agglomeration, with the green impact strength test and the indurated compressive strength test being used to determine if these pulping liquors still outperform bentonite when these big pieces of equipment are used. And part of that is also determining at which point in the process do you want to introduce these pulping liquors. So there's several options. You can either decrease the moisture content of these pulping liquors right at the start and introduce them during the milling stage, or you can actually only introduce them in the disc pelletizers or the boiling mills themselves in place of the moisture. And all of these will also obviously affect the cost and transport and stuff like that of these pellets. So it is also necessary to do a techno-economic evaluation depending on which of these options actually works best for the industrial scale equipment. So additional research should also be done into the extent that these pulping liquors affect the oxidation and reduction of these pellets, and importantly also if they affect the smelting of the chromite in the submerged arc furnaces in any way, be that either positive or negative. Now, if all of these results prove to be positive as well, and it proves that these pulping liquors can be used for industrial scale equipment, it provides the chromite industry with an alternative option to bentonite. This is a very good thing because there have been fluctuations in the supply of bentonite in the past, and there's been times when the chromite industry have had shortages and have desperately looked for other binders that they could use. So if anything like that happens in the future, pulping liquors can be used if they're found to be suitable. Alternatively, also, if these pulping liquors actually are found to be cheaper than bentonite in a techno-economic evaluation, it could mean that the chromite industry can actually switch over to pulping liquors more permanently and change an entire pelletization plant over to pulping liquors. Now, this would obviously be very good for the paper and pulp industry because it would mean that there is a alternative higher value use for these pulping liquors that a lot of times are simply burnt for either energy recovery or cooking chemicals recovery. So that is the end of my presentation today. I'd just like to thank everyone for their time, and if you have any questions, please don't hesitate to ask.
Thank you, Henry. Yeah, well done. Sorry for the technical glitch at the beginning there, but you recovered well, and I think we worked well together as a team. Does anybody have a question? Nelson, over to you.
Thanks, Andrew, for the wonderful work. Just remind me again, the samples that you received, were they all liquid samples?
So three of them were liquid samples. The only one that I received as a spray dried powder was the sodium lignosulfonate.
Okay, so and then when you charge the lignin onto the chromate, what did you correct for the?
So all of my different pellets are produced with the exact same moisture content. So for the case of the sodium lignosulfonate, I added enough moisture. So every pellet was made with 10% moisture. So in the case where the pulping liquors didn't have enough moisture, I added a bit more water, and obviously in the case of the sodium lignosulfonate, I had to add all of the water.
Okay, but you didn't consider the fact that the different lignins obviously had different inorganic to organic ratio, and therefore, let's call it given the same opportunity. But because obviously, I mean, the soda lignin and the kraft lignin as well as the lignosulfonate, if you look at the organic to inorganic ratio, that those are different.
Yeah, so the mass percentages that I used are just based off of solids percentage. So whether that's inorganic or organic.
Total solids. Okay.
Yeah, it's just total solids, yes.
Okay. All right. And then my last question is also obviously more just a check, because obviously the kraft lignin will have been more alkaline versus the sodium lignosulfonate as well as the magnesium base, which is more acidic. Have you looked into the effect of pH? I mean, it is the effect anyway. Is that come into play here in terms of affecting your results?
From the research that I did, pH doesn't affect anything that I could see in these pre-reduction steps. But I mean, it might have an effect maybe during the smelting, but obviously because my project my scope was before that, I didn't look into that too much. But from what I could find, the pH shouldn't affect anything negatively.
Yeah, interesting for me just to look at the data and see if there's an impact, as well as, of course, the solids. Good, thanks.
Thanks, Nelson. I don't see any other questions. Wait, one more. Herman Parkita, you're welcome to ask your question.
Good morning, Henry. Maybe more a comment than a question. Have you correlated any of your physical test results with the physical appearance of those specimens that you prepared and that you tested, maybe under a scanning electron microscope or with different porosity measurements, something like that?
Yes, so at the moment, I'm busy looking at results for the porosities. I'll put them in a CT scanner to get different porosities, but at the moment I'm having a problem with that the CT scanner only picks up the internal porosity and not the closed porosity of the pellets and not the open porosity. So I'm busy looking at that. I don't have a concrete answer for that just yet. But yeah, I'm considering that as well at the moment.
So Henry, you kind of proposed at the end that one should do a cost comparison between spent sulfite liquor or spent liquors and the bentonite. In our discussions with the chrome producers, they kind of indicated that bentonite is a very small portion of their operating cost. So ultimately, there might be non-economic reasons to consider organic binders, carbon wetting and other benefits within the process. Could you maybe elaborate on those? So non-commercial reasons, non-economic or financial reasons for why they would consider organic binders.
Yeah, so with the binder itself, obviously bentonite isn't the most expensive. It is still a relative cost. Because pulping liquors are a waste, there is a chance that it is cheaper than the bentonite just for that. But there is also a chance that they can at least partially replace the reductants that they also use. So at the moment they use stuff like coke and anthracite. And obviously because these pulping liquors do have some fixed carbon, they can partially replace that as well, also cutting costs there. They can't replace it completely because unfortunately the lignins don't have that high of a fixed carbon content. But there's also with the stuff like carbon wetting and all of that, I haven't been able to look into that too much as well, but there's so much stuff that during the production of these pellets could play a role. But unfortunately, it is obviously hard to do that on a lab scale because I don't know exactly all of the things that go into the nitty-gritty of the industrial processes, which is obviously stuff that would also have to be investigated during the further research.
Hello everyone. My project was about the drying of nanocellulose with xanthan gum as a capping agent and its use for the reinforcement of a Mura thermoplastic starch. I know it's a lot of big words, but hopefully by the end of the presentation, everyone will be clear on what that exactly means. So my name is Jan Hoek. I studied chemical engineering, mainly because I really love chemistry and chemical engineers tend to be paid a bit better than chemists. I did my master's mainly because the Pumps opportunity was presented to me and I just took it. And I specialized in polymer science, primarily because I was given the opportunity to work with Professor Walter Fokker, which is arguably the most intelligent man I've ever met. So I didn't go into polymer science for the science, but rather for the man. But I don't regret it. It was an absolute blessing working for him. And yeah, so this is just a short overview of everything that I'm going to cover. So to give a backstory, this is basically why I did what I did. So what you're looking at is starch being turned into plastic using a twin screw extruder. Now, as you can see, it is bubbling, which it isn't supposed to do, but I'll get to why that's happening later. So when you turn starch into plastic, you create something called thermoplastic starch. It is completely biodegradable and renewable, but unfortunately, it's very fragile. It has very weak mechanical properties. Now, a way you can remediate this is by adding a filler. The one I specifically looked at is nanocellulose, which is how my project connects to the pulp and paper industry. Nanocellulose is a high-value product produced from cellulose that has incredible mechanical properties. And when you add nanocellulose to any polymer, it imbues the polymer with its mechanical properties, greatly increasing tensile strength and stiffness. But there's a problem. Nanocellulose has a lot of water in it. The nanocellulose supplied to me kindly by SAPI is only 8% nanocellulose. All the rest is water. So that is why my starch plastic is boiling, is because there's so much water that is being added with it when I add nanocellulose that when it comes out of the extruder, it just simply starts to boil. Now, this is a big problem. If you're shipping a ton of nanocellulose, you're shipping 11 tons of water with it. And as you can see, water doesn't play nice with most polymers. So you might be wondering, why don't you just dry the nanocellulose? Well, it's because of a process called hornification. Hornification is the irreversible agglomeration of cellulose when it is dried. So here's a basic explanation of how it works. Here we have two cellulose fibers with water in between it. If you now go and add heat to try and dry the cellulose, the water is removed, and the cellulose fibers move closer together. And when they do so, they form hydrogen bonds in between each other. And these bonds are so strong, you'll need to apply almost the same amount of mechanical energy to try and separate them as what you did when you initially made the nanocellulose, which defeats the point of making it in the first place. So this is my solution. I wanted to see if I add xanthan gum, a hydrocolloid, as an additive, if it might be able to produce redispersible dried nanocellulose. Now, xanthan gum is a hydrocolloid. Hydrocolloids are thickeners. It's things such as agar-agar, gelatin, or pectin. But xanthan is like the uber colloid. Its thickening ability is incredible, much stronger than the majority of other thickeners. And it has a bunch of other very unique properties. So the basic idea or hypothesis, one could say, is you add the xanthan. You then apply heat. And as you apply heat and the water evaporates, the fibers move closer together. But hopefully, the xanthan is in between the nanocellulose. And when bonds form, the bonds rather form between the cellulose and xanthan, not between the cellulose and cellulose. And hopefully, these bonds are then much weaker. So I threw a bunch of different characterization methods at it to try and prove that when adding xanthan gum, you can create redispersible nanocellulose. We use things such as rheology, turbidimetry, colloidal stability analysis, but nothing shows it better than just some pure images. So here are 4 scanning electron microscopy images. In the left-hand corner, we have pure cellulose fibers that have never been dried. You'll see some crystals in the image. Please ignore them. A bit complicated why they're there. But as you can see, fibers are generally apart, quite small. Everything is good. In the right-hand corner, we have pure xanthan gum. Now, as far as I know, it's the first images of pure xanthan gum ever taken. I know most people don't care about it, but since it's like a year of my life, I think it's very, very interesting. And here in the left-hand corner, we have dried nanocellulose that's been redispersed in water. And as you can see, the agglomerate is massive. It's over 2 micrometers, which is larger than what a lot of the fibers are actually long, which goes to show hornification is happening and not very easy to get them apart. But in the right-hand corner, we have a sample with 15% xanthan added prior to drying that's then redispersed in water. And as you can see, we were able to fully redisperse the nanocellulose in water, proving the hypothesis that xanthan gum is effective at preventing hornification. So a thing I then further did was analyze what is the effect of xanthan gum on nanocellulose as a reinforcer. This is something that has not been really looked at most of the research I've done. Most works just look at can they produce dried redispersible nanocellulose and not what is the additive doing to the nanocellulose afterwards. So to basically explain how this works, let me just quickly get the laser pointer. You basically have your polymer films, which in this case was thermoplastic starch, which is then placed between 2 clamps. And these 2 clamps are then moved apart at a constant rate. And the machine then measures how much force does it need to apply to continue to pull this polymer apart at that constant rate. So essentially what you're looking at here, elongation is how much has the polymer been stretched. And then the tensile stress is the force that's being applied at that point of elongation. Okay, so as you can see, the blue one here is the pure thermoplastic starch, no filler in. As you can see, it's quite weak. It has a tensile strength of about 5.4 megapascal, which is half of low density polyethylene, which is one of the much weaker polymers used in the industry. Now, xanthan low is thermoplastic starch with 1.25% xanthan added. As you can see, not much of a change that's happening, but xanthan high, which is thermoplastic starch with 2.5% xanthan added, is much stronger, much stiffer. And why did this happen? Well, the theory is that once you hit a certain point or a certain concentration of xanthan, you have a continuous network that forms throughout the polymer matrix. And then it can basically reinforce the polymer as a cohesive unit. Whereas if you have this on continuous networks, they don't work together, and you have certain points that are weak links that essentially will behave as pure thermoplastic starch. Now, the NC sample is thermoplastic starch with 5% nanocellulose added to it. As you can see, very strong, very stiff, very good. And then you have the nanocellulose and xanthan sample. Here we added 5% nanocellulose with 1.25% xanthan to the thermoplastic starch. As you can see, incredible strength. It's about 23 megapascals is the tensile strength that it had. That is basically as strong as polypropylene, which is what like your cool drink bottle tops are made of. Much, much, much stronger. Very good properties. I don't want to brag, but it's like the best results I've seen in out of the research I've done. And to also emphasize, the nanocellulose xanthan sample is made from previously dried nanocellulose and xanthan, and it was the strongest sample of them all. We did do tests comparing non-dried nanocellulose and xanthan with dried and then redispersed nanocellulose and xanthan. There isn't that much of a difference. Nothing we can say conclusive about it. It's most likely because cellulose and starch is very compatible, meaning that to see what the effect of agglomeration really is on the reinforcement, you'll most likely need to use a less compatible polymer, something like polylactic acid. So, to conclude, xanthan gum does limit hornification and is effective at producing redispersible nanocellulose. And xanthan gum adds to the reinforcement properties of nanocellulose in a synergistic manner, meaning it doesn't detract but add to the reinforcement qualities. So further, we need to test lower xanthan gum concentrations. The lowest I went was 15%. It needs to be tested in other polymers, especially less compatible ones. And there needs to be comparisons done to other hydrocolloids. Things such as carboxymethylcellulose, for instance, is one that's also commonly used. Thank you very much for listening, and you can ask your questions.
Yeah, well done, Zian. I mean, this is fantastic work.
Thank you, sir.
How much of this has to do with the fact that in all these three polymers are call it glucose polymers, and obviously they create synergistic compatibility. I mean, if you look at glucose, if you look at cellulose, which is a much more linear polymer of glucose versus starch, which is branched, versus a xanthan gum, which is even further branched. And I think the use of xanthan gum in this application is quite ideal, because then it almost like partition that starch molecules and nanocellulose molecules to allow more gaps in between them to avoid agglomeration, which is what you achieved. I'm just fascinated. Is that much of this to do with the three polymers being more compatible, as well as just really a good behavior that we see with nanocellulose? I mean, how much of that is nanocellulose, but how much of it is really
so xanthan gum is actually the most linear of them all. It is extremely stiff. Yeah, as you can see in the images, it tends to stay very straight. So the thing we saw in our microscopy images is that when you add nanocellulose and xanthan together, they tend to form these very intricate bundles between each other. And I believe that makes it that good of a reinforcer, because you have this very high level of interconnection. So when we did statistical analysis, we did see a positive interaction effect between nanocellulose and xanthan, meaning that they add more to the tensile strength that is just more than purely additive. The high compatibility, meaning they all basically have glucose backbones. So that definitely helps a lot. There isn't incompatibility. You won't get phase separation or anything like that. So that does help a lot. But I don't think that xanthan adds more by making them more compatible. I think it adds by making a more connective network within the matrix.
And just one last comment about solubility. I mean, I think the other two polymers are more soluble, and then cellulose is not. I assume you're doing this study in aqueous medium.
Yeah. So xanthan is very, very soluble in water, and we did see that when you add xanthan, your sedimentation is much less reduced when we did colloidal stability analysis. Yeah. So you do see that it tends to sediment much slower, like days, basically. So yeah, so that definitely does help.
Yeah, but nanocellular doesn't dissolve, unfortunately. So
Yeah, yeah.
okay, thanks, Ian. Well done.
Pleasure, Nelson.
Thank you, Nelson. Rosalind.
Sure, just a question. So I presume the bubbles that we saw when you were extruding the starch-based polymer were the water that was evaporating off.
Yes, so basically, so in the extruder you have like 20 bar of pressure, essentially. So the water is then still in liquid form, but the moment it comes out, it like nucleates and then just go.
Have you been able to test your new xanthan starch polymer to see if it extrudes?
I did it once and then the extruder stopped because its shear viscosity so high that like our little lab extruder couldn't handle it. So yeah, so I still need to, like, that's unfortunately something that needs to be worked around. So yeah.
Do you know if commercial extruders would have the hydraulic pressure to force it through?
Most likely. Yeah, I don't see why not. It also depends on, I was a bit ambitious. I added maybe a bit too much initially. But when it happened the first time, I was like just too scared to try again. So yeah. It's
super interesting. Thank you.
Yeah, sometimes you've got to break stuff to make stuff. So thank you, Zian, and yeah, thank you to all our students. Can I perhaps get you all on screen again, and then we will hand over to the lady that makes it all happen behind the scenes, Julie Borland. She is our the lead on the Master's Research and Bursary program, and she is the mastermind behind a lot of all of these students and helps them along. So yeah, Julie, over to you to do the closing remarks.
Thank you. And firstly, I'd like to thank all our students. They were excellent work and excellent presentations from you all. And I'm sure that we're going to go away really inspired by your enthusiasm and dedication to the pursuit of knowledge. It definitely came across through your presentation, so thank you for that. And we look forward to you finalizing your masters and joining us in the sector as new engineers. So keep going, you're nearly there. And then I would like to thank everyone who participates in the active discussion that we've had today. We're always grateful for the support and assistance to the program and to our students, and it really makes it very successful. So thanks once again to everyone, and we look forward to seeing you online again next year. So have a good day going forward. So thanks from me.